to go back to this equation, I'm going to write out all the components. I want to be painfully explicit because I'm going to show you some details that aren't really, when you read a book or look at paper on this, there's sometimes an abusive notation, and I want to make you aware of it. Not sometimes, there's almost always an abusive notation. Right, so this is the first equation, and it just comes from this, right? So both I and j go from 1 to 3, right? So I just start off with, I choose I equal to 1, right? So everywhere you see an I put a 1. But then I have a summation over j, right? Remember Einstein notation. Anytime you see a repeated indice, so here you have, partial u I partial xi times dx, partial xj times dxj, that's a repeated indice, so that implies a summation. So that's what I'm doing, I'm expanding the summation there, right? And so then I'm going to choose I equal to 2 and do the same thing. So now I'm choosing I equal to 3 and expanding the summation. So this is nothing more than that equation. It's just all expanded out, right? So it may give you a little more insight into the initial notation. Anytime you have a free indice, one that's not repeated, that's an equation, okay? Anytime you have a repeated indice, that's a sum, right? So now you can probably see why we like initial notation, because this one little compact equation is equivalent to all that other stuff. So again, just painfully explicit here, but we can write this in a matrix, a more matrix vector type equation. right? Everybody familiar with that notation? Right? Just sort of linear algebra type notation, matrix vector. All right, now let's make some observations about what we have here. Remember, U is a vector. So it has components U1 in the E1 direction, U2 in the E2 direction, U3 in the E3 direction, right? Does anybody remember from Calc 3 what the gradient operator is? Like if I typically use this notation, and maybe I'll, just to be very explicit, we'll say we're going to take the gradient with respect to big X of something. What does that look like? So, right, if what the something is, right, if it's what's in that dot there, right, whatever it is, like if that's a scalar and we take the gradient of it, what do we get? A vector. And if it's a vector and we take the gradient of that, what do we get? A dyad, right? A second order tensor or a matrix, right? But so, explicitly what that operator is like this. Right? So let's just to see what happens, let's put U into that. Let's take the gradient of U with respect to big X and write out everything. Right? So the gradient of U, where U is a vector, you have E1 partial U1 E1 partial X1 partial U2 E2 partial and I think everybody can see that this is just going to be the same thing, right? We have that thing. Now, I was a little bit explicit there, and that I put that this derivative has to be taken on the product U1 E1, because in general E1 could be a function. And that would be the case if you had curvilinear coordinates or something. In what we're talking about in this class, the E1s, like I mentioned last time, they're just constants. We're talking about Cartesian coordinates. So they're just constants, so you could also move them outside, right? And so, like was mentioned, there's something called a dyad, which is also a second order tensor. It sort of has the definition, a dyad or second order tensor A is the summation over I, summation over J, AI, BJ, EI, EJ, where E's are basis functions, right? So based on that, if we write this in what the gradient of U is in like dyadic notation, so the gradient of U, just pulling out terms of our matrix up here, right? Because we have E1, 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 E2, E1, E3. Sort of the indices of the E's tell you where those terms go in the matrix, right? If it's E1, E1, then it's the 1, 1 location in the matrix, first row, first column. If it's E1, E2, it's first row, second column. If it's E1, E3, it's first row, third column, right? And then just going to pull those coefficients out. So if we do that, what we'll have is U1, X1, U2, I'm sorry, U2, whoa, I made a mistake. These should be not all the same. I was lazy there. I'd written it all the way in my notes. This is 1, 1, 2. I guess I'll just have to write it all out. All right, sorry about that. All right, so now let's pull out the coefficients. And we have that. Okay. Now, it's going to be a little tricky, but just look at this thing, the gradient of U, okay? And just remember that in the gradient, in the real gradient of U, using Calc 3 definitions, right? I mean, this, if you pull up any calculus textbook, that's what is going to give you the definition of a gradient with respect to some variable x or vector x, okay? So, and then of course U is just a vector. Right? So using Calc 3 definitions for the gradient of U, this is what you get, okay? And I want you to just look at this and notice that on the components of U's, they increase along the rows where the partial derivative you're taking with respect to is constant. It's the same as the row number, right? So we have partial x1, 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 partial x2, 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 right? It's the same as the row number, okay? So look at that real carefully because I got to go back a slide, all right? If we go back a slide, look at this. What do we have there? It's almost the same thing, right? It's almost the gradient of U, but it's the gradient of U transposed, okay? So I went through all this trouble to basically point out that, well, that if we go back and we look at this equation, right, and if we want to write this in vector form, right, if we want to write this in vector form, or if we want to write what f is, right, so we know that Fij is delta ij plus ui xj, right? That's what it is in additional notation, and that's another reason to be comfortable using it, because you can never be wrong when you use additional notation. But let's say I want to write that in a matrix notation. What is the equation? Now, F is a matrix. This guy is the identity matrix, and what's that? You just said it. It's the transpose of the deformation gradient. In other books that actually take the care to make this definition correct, namely is sort of one of the most famous, it's one of the references on the syllabus, but it's a book by Malvern on continuum mechanics, which was written in '69, which is sort of where we get all the conventions of little x, big X, F. It's sort of the standard notation for continuum mechanics, and it's a classic textbook on continuum mechanics. In that book, he takes the care to note that it's the transpose of the deformation gradient, but he introduces a little bit different notation in that he puts the gradient operator on the other side of the U to indicate the transpose of the deformation gradient. Yeah?
Can you explain what the delta means again?
The delta is a gradient operator. It's the Kronecker delta. Yeah, I'll come back to that. Okay. The Kronecker delta is just a special function that when I is 1 when I equals to j, and it's 0 otherwise. Otherwise is when I not equal to j. Right? So in Cartesian coordinates in 3 dimensions, it's the identity matrix, right? It's 1 along the diagonal when I and j are basically rows and columns, right? So it's a special function in additional notation, right? Okay, so yeah, I just went through all that trouble to say that, the deformation gradient is I plus the transpose of the gradient of U. And the reason I went through all that trouble, and you may not know, but when you look in probably 75 or 80% of the papers out there, and many of the textbooks, what you'll see is that the deformation gradient is I plus the gradient of U. Well, that may be true if they redefine the gradient operator to be non-standard, not what it is in Calculus 3 everywhere. But to use the standard definition of the gradient operator, it's as I have it written.